Thanks for the invitation. My pleasure to speak in the conference in honor of Korsha. And yeah, so my colloquium style talk related to the work of Korsha is, well, really kind of about the end point, you could say, of a story that started with my thesis work with Korsha. So this is, yeah, thank you to him for introducing me to this in the first place. Okay, so, right, the LMNP for excellent threefolds. So, well, at first I just want to make a standing assumption, which, well, to make sense of things I'll say later. So a variety over a ring R is an integral scheme which is of separated and finite type over R. Okay, so I guess just to be clear, I'm not assuming geometrically anything, just integral scheme separate finite type over R. And if I talk about V, V is spec R, and this R is going to just be the base. Okay, so, well, firstly, first part of my talk was just going to be an introduction to, well, what is the log minimal model program? So we've had several introductions to that already, so I guess I'll be brief. I guess, well, in particular, I guess you could watch Professor Morris' talk or Professor Arroyo's talk from earlier, then when you'll get these intro. I guess I might use some differing terminology to Professor Morris' talk. Okay, so I guess I just want to maybe repeat some things, especially because I'm doing everything in this relative setup for this ring spec R rather than over a field, so that changes a few things which I just need to maybe point out. So in particular, well, the thrust of my talk is that the LMNP works for excellent threefolds, and so in order to explain that, I need to say exactly what I mean by saying the LMNP works in some situation. Okay, so I guess I'll introduce 4 ingredients of the LMNP. So 4 main things you need to say LMNP works. And the first one is the cone theorem. Sorry, let me just hand position slightly odd. Put some stuff under here. Okay, cone theorem. So, well, this is saying, well, you have this cone of curves and look at the shape of the k negative part. And in particular, well, everything's relative to this V. So I'm going to be looking at the vector space of curves which are vertical over this V. So this is the R vector space of 1 cycles which are vertical over V. Then modulo numerical equivalence. Okay, and then we have inside this the effective cone, the closure of the cone of effective 1 cycles. Okay, so then the cone theorem, and I say theorem because I'm not giving you any assumptions. I don't tell you what you need to actually assume about, say, X and V to make it true. Okay, so it essentially says, well, the part of this effective cone on which Kx is negative, well, has only isolated extremal rays. And each of these contains well, class of some 1 cycle. Each contains a rational curve. In particular, just contains a curve. Okay, so this means you have some cone of your 1 cycles, like so. And inside this vector space, you have Cartier divisors giving linear functionals. Here's the one for Kx being 0, meaning on the side of facing me, this is where it's negative. And then on the other side, this cone can look like anything, but where Kx is negative, it looks kind of pointy, and you have these extremal rays. Okay, so ingredient 1 says, well, this cone theorem should work, and you get these isolated extreme arrays where kx is negative. Okay, so the point is we want to contract the curves in these extreme arrays. So that brings me to the ingredient 2, which is, well, base point freeness or contraction theorem. Okay, so base point free theorem says, well, roughly, base point free theorem, if A is ample, this isn't the full statement, it's just enough for what we actually need right now. So if A is ample and kx plus A is NAF, then kx plus A is semi-ample. Okay, so the point is now adding on this ample divisor to this hyperplane in the space of curves lets you move this functional forward in such a way that it will intersect at exactly one of these extreme arrays, meaning when you take the map given by the semi-ample divisor, it's going to contract only the curves which are inside the array that we're interested in contracting. Okay, so in particular, you should see this, well, if this extreme array is called gamma, gamma would be kx plus A pup. Right now, I'm being incredibly vague about what I'm working over because I want to come back to that in a bit. Okay, so I just said R is a ring, and then if MMP works over R, this is what you want. If it doesn't, then yeah, it won't. Okay, so right, this is ingredient 2. We want this base point free theorem. I put the statement up here because this is really the one we'll focus on most in this talk. Okay, but then, well, this tells us what we need. We want to contract this extreme array. Okay, and then, well, we need to be able to do something with the contraction. So, well, ingredient 3 is that flips have to exist. Okay, I won't say too much about what flips are because I'm not talking about flips, and you've heard that already in this conference. So, well, the idea is just that you're going to split into cases based on what this contraction does. And your cases are, well, case 1 is if, well, I mean, I should introduce what this contraction is, I guess. So kx plus A gives you f from x to some variety z. This is a contraction of the curves in the extreme array. So then case 1 is going to be if the dimension has dropped. Okay, if the dimension has dropped, this is a Fano fibration central model. And well, in particular, it's a special one called a Mori fiber space, which means that, well, rho x over z is 1. All the curves are numerically equivalent to multiples of each other. Okay, and this is an output of the MMP. Okay, then you have case 2 where the thing is birational. So if this is equality, then you get 2 subcases, case A and case B. Case A is divisorial contraction. So F contracts the divisor. In that case, the Z is relatively nice, and you can continue, replace it with this Z, replace X with Z and continue. And in the other cases, if, well, you don't have a divisorial contraction, that means you're contracting something smaller. So codimension of the exceptional locus of F is less than 1. Then, well, the Z is not nice, and instead you have to use a flip and continue from the flip. Okay, but I'm not going to actually say what a flip is. It's just this other thing you have to have. Okay, so the MMP is this process I've described right here. You start off with your variety. You, well, take an extreme array in its kx negative extreme array. You do the contraction of it. You see which case you're in. If you get in this case, you say you're done. If you haven't, then you replace x with whatever you get out from this process, and then continue. Okay, and then, well, if that terminates, you'll end up with one of 2 things. But, well, this brings me to ingredient 4, which is that you have to be able to stop the process. So there has to be some sequence, some way to choose the extreme arrays, which ensures that you're going to end some sequence of steps, in particular flips, because divisorial contractions terminate not so hard. Some sequence of steps always terminates. Okay, and then, well, that brings me to the outcome. So if it terminates with this Mori-Faber space we've already seen, then that is one of the ways it can terminate. The other way it can terminate is you just run out of extremal rays to try to contract. That is, you run out of kx negative extremal rays. The only way that can happen by the cone theorem is if there's no kx negative curves at all, in which case you end up with kx nef, meaning we call this a log minimal model. Okay, so you end up with one of these two outcomes. Okay, so right, there's the four ingredients you need to say that MMP works. So if I say MMP works, I must mean all of these four things happens. And I guess I should say, well, I don't say everything terminates here, but in order to get to one of the things for a particular variety, you just need to know some, not necessarily all. Okay, but some kind of technical additions I need to make. So as we've seen, you can't just assume that the x is smooth because you don't get to keep that assumption. So x is, well, singular, and the kind of singularities I'll be talking about are Karmata log terminal, KLT. But for the point of view of the talk, if you just replace that everywhere it appears with smooth, you'll be wrong, but won't understand anything wrong. So this is kind of okay. Okay, the singularities don't matter too much. Okay, what will matter more is the pairs. Okay, so that means that instead of working with kx, where I said kx before, you're really looking at kx plus b for some boundary b. And this is some divisor, which is divisor with coefficients between 0 and 1, such that this kx plus b is q Cartier. Okay, and then you're going to have some conditions that on singularities of this thing instead of just the x, but again, I don't really care about the singularities. You can just pretend that means a simple normal crossing. Again, don't worry about the singularities, but it matters that this b is here. Okay, but all that means is for everything I've just said, wherever there was a kx, just replace it with a b. So there'll be a b in here and some b's in the cone theorem. Okay, again, pretty harmless. Okay, but the reason we want these pairs is the adjunction formula. So I'll just write that down, adjunction. So if xb is DLT, since I'm allowed coefficient 1, KLT is not necessarily enough. I want divisorially log terminal, but again, just pretend that means simple normal crossing. Okay, so is DLT, and S is a component of B of coefficient 1. That means we can restrict to it with adjunction formula. So then there is a boundary, or rather a pair, S, B sub S, such that Kx plus B restricted to S is, well, at least linear equivalent to Ks plus Bs. Okay, so then the point here is you're allowed to then talk about things by induction. You've got something of lower dimension here, which you restrict to, and you put yourself in the same situation as you had before. Only now, well, this is why the pair is necessary, because even if you don't start with 1, if you just start with Kx plus S, this 1 will appear here in general. Yep, I think you probably will, right? So everywhere I'm going to be talking about resolution either holds or it's going to be an assumption of the theorem. So I'll come back to resolution, but in general, what we know is resolution always holds in dimension 3. And then, well, modulo some small technical difficulties, it always holds in dimension 3. So anything to do with KLT, DLT just works exactly the same until you're in dimension 4, and then you have to be careful about exactly what that means. Okay, so that was well, intro to what is the MMP. So secondly, well, I want to come back to this R. What is the R? So what R's do we want? Okay, it doesn't want me to write R, but there's an R here. Okay, so I'll just go back. What is R? It's just supposed to be the base. So every curve that we contract is vertical over this spec R. This V is spec R, and every flip, divisorial contraction, Mori fiber space has happened relative to spec R. So really, this all has V over V, which is spec R underneath it. Okay, so then the question is, which of these do we want to do this process over? So firstly, just what do we want, and then what do we need? So first, what do we want? I mean, we want the complex numbers, of course. But then you can just say, well, any algebraically closed field, so any k bar, now it can be positive characteristic. But yeah, then this is a classical one. Okay, but then we can ask for some other things like, well, is our finite type over one of those? So finite type over k bar. Okay, that turns out to be important for constructing all the moduli spaces and that kind of thing. Your moduli space is like talking about families of these varieties over some base, which is finite type over an algebraically closed field. So to construct them, you need to, well, be doing MMPs over varieties. Okay, so that's something we also need in characteristic 0. Okay, but number 3, well, in doing this kind of relative variety version, you see you have the base and then you have the family, and often what you'll do is, well, these fibers all look roughly the same, they all look like varieties, so let's just restrict to one and do something there by induction. But in positive characteristic, you don't get to do that because of these, well, spec K, X, Y, S, T, mod S, X square plus Ty square plus 1 in characteristic 2. Okay, then if you look at the fibers of this, they're all non-reduced, so you can't restrict to that. But instead, the thing you try to do is restrict to its generic fiber, which is a regular variety, which is well behaved unless you try and extend the ground field to the algebraic closure, in which case it becomes non-reduced again. Okay, so in order to do that kind of induction argument, you're going to want to work on, well, the fraction fields of 2. Okay, and in characteristic 0, that doesn't add anything new. You just base change to the algebraic closure, and you basically oversee again. You can just ignore the difference for most practical purposes. But here you can't, just because these non-reduced guys. Okay, so then, well, this is all coming from algebraic geometry, but then you can ask for things like, well, the integers, localizations of those, arithmetic rings, if you want to do number theory. Doing MMP for number theorists can be helpful. Okay, so then, well, I guess I don't need to motivate number theory. This is a reasonable thing to ask for, to be able to do things in arithmetic families. Okay, and then 5, well, let's just say localizations of all the above. Okay, another fairly natural geometric thing you can try to do to, well, have some other useful situation. Okay, you'll see why that actually is necessary rather than just, well, working on one of those later. But okay, so here kind of is everything that I would say, well, we really want to be able to do MMP over. Okay. And I guess, well, what I can again point out is kind of if you're working over C, there's not that much difference between any of these. You can just do everything kind of over the ground field and then go from there. But in positive characteristic also C, you don't get to do that. Okay, so this was what we kind of want to have. And then, but any questions before I move on? Okay, so that's what we want R to be. What kind of R's do we want to be able to use? Now, what kind of R's do we need? So what kind of properties do we need R to have any hope of succeeding, to even think about trying to do those things. Okay, so well, firstly, I keep talking about kx, so you want some kind of canonical divisor to be useful and make sense, which kind of means you need some kind of duality going on. So, well, R has to have a dualizing complex to kind of make that useful. So R has to have a dualizing complex. Okay, so that's kind of a restriction on its singularities. Okay, but then, well, to talk about things like, well, whether or not we are codimension 1, etc., dimension needs to be sensible. So dimension should be sensible. So you want Noetherian or universally catenary to say dimension is sensible. Another thing we really want is, well, resolution of singularities. So resolution of singularities, you kind of need to have much hope of doing much of the MMP stuff I just described, the 4 ingredients, at least as we currently know how to do it. So, well, what do we need? Resolution should be plausible. I mean, conjecturally possible, if not actually known. Okay. So at the very least, you don't want to have to make a hypothesis on a thing that you know can't possibly be true. So, okay, resolution should be plausible. And finally, well, if we start with something that we want to be able to use, we want to kind of be able to do the stuff we could already do up here to it. So you want to be able to take fraction fields, localizations, things finite type of your ring, and still be able to do the stuff. So a property of R should be stable under finite type and localization. Okay, so here we have essentially 4 kind of requirements of the ring to hope to be able to do this stuff. Okay. Okay, so it turns out these 4 restrictions kind of say, well, you want R to be an excellent ring with a dualizing complex. Okay, so, well, excellent ring, I don't want to define it because the definition is really technical and doesn't really have that much to do with what we actually do. But the point is, excellent ensures you have, well, these 3 things. It includes this universally catenary, so dimension is sensible. Resolution is plausible because this is what excellent was originally kind of introduced for. It's the Grothendieck conjecture. This is what it should be if and only if for resolutions to exist over R. And then, well, excellent rings have this property that the property is stable under finite type localization. Okay, so you can think this is in a sense the maximal assumption you can hope to use for doing MMP. Yep. So conjecturally possible, not known. Okay, so right. Dimension 3, you know it exists. Dimension 4, you don't know it exists, but it's a reasonable thing to say. Assume resolution holds, then we get these consequences, which you certainly can't do without. I mean, it's known that if you're not excellent, resolutions don't exist. I guess is the point here. Okay, but I should make a point, I guess, of saying resolution is known in dimension 3. So nothing in dimension 3 is going to be contingent on resolution. Okay, and that's in all possible situations, so excellent, the full generality. Okay, any more questions? Okay, so section 3, LMMP for threefolds. So this is really what we've been doing, MMP for dimension 3. So I guess the theorem, which is, well, not necessarily my theorem, but it's just the conglomeration of all the stuff that's been done, says let R be an excellent ring with dualizing complex, and which has no residue characteristics 2, 3, and 5. Okay, so then the element P works for threefold pairs which are projective over R, for KLT threefold pairs which are projective over R. Okay, and I should say this dimension assumption is global dimension, so it's not dimension 3 on top of the dimension of R, it's just dimension 3 over the base. But dimension is the global dimension of the scheme. Okay, so right, we know essentially now the MMP works away from these 3 characteristics if you're, well, in dimension 3. Okay, so this is the, well, theorem, and now I want to say, well, what is the history, where did this come from, and try and at least write down as many names as I can, say how this came about. So sorry for any contributions I missed, because there's so many it couldn't possibly be entirely complete, but at least, okay, so in the various situations, I guess, well, we start with the MMP for threefolds, so, well, over the complex numbers, this is where the whole story started in the form I described. So for dimension 3, over the complex numbers, this is, well, where everything was formulated in the 80s by many people, including Professor Mori, Shokurov, Kolar, Kamata, Reed, and well, many more contributions too. Okay, but the point is this is the kind of original MMP setup. Okay, and in dimension 3, I'm always talking about dimension 3, but at this point I'll say, well, because of BCHM, who are all in the audience right now, most of it works in higher dimensions too. So works in all dimensions over C if the boundary is big. Okay, which covers general type log Fano cases. Okay, but then really this is going about, well, positive characteristic arithmetic stuff. So where did that happen? So I guess the positive characteristic story was the, well, more recent stuff. So if we're looking at algebraically closed fields in characteristic P greater than 5, this, well, I should mention work of Kiel, but then the kind of more recent work started with the work of Hicken-Zhu, which really said that flips exist in, well, some where you make some assumption on the boundary being standard coefficients, and this is where this P greater than 5 appeared. So no residue characteristic 2, 3, 5. I'm not going to talk about flips, so I won't say too much about that, but this is well, where this P greater than 5 first appeared. Okay, so then we have the work of Korcher, extending the flip existence into, well, all arbitrary boundaries without assuming the standard coefficients. And then my work with Korcher in my thesis, which was about, well, showing that Mori fiber spaces exist in this case, so that you can get an MMP which terminates, and base point free theorem. Okay, so right, this is the algebraically closed field story. I guess possibly I should also mention Kashini Tanaka-Zhu, I think that covers, well, most. Okay, so, right, this says, well, everything works over algebraically closed fields. Okay, then we have, well, other situations. So if you're not over an algebraically closed field, so K perfect, it's by Gongyo, Nakamura, and Tanaka. And so then, well, the function field case, so K imperfect. Okay, I'm just going to also stop writing p greater than 5 everywhere, but you should consider a p greater than 5 to be basically in force for the rest of the talk at this point. So wherever there's a positive characteristic thing, that it is greater than 5. Okay, so K is imperfect. This is due to myself and Omprakash Das. At least this was if the Kx plus B is pseudo-effective, meaning you're expecting to find a log minimal model. Okay, so we didn't finish the Mori fiber space case, well, because, well, there was something missing, which I'll get back to later. Okay, so this is, well, all over a field. Then we have this arithmetic stuff. Okay, so the arithmetic situation, he doesn't like me writing R's today. Excellent. And dimension greater than 0. Okay, so this is basically the relative situation where you're just not over a field, anything where you're not over a field. So all of those situations, which means this had better be surjective. Okay, and, well, again, p greater than 5, all p is greater than 5 if you're over spec z, so z 1 over 30, not including the small primes. Okay, so this was due to, well, Kawamata did the semi-stable case in 94. Then the recent stuff, so Takamatsu, Yoshikawa, and the 7 author, so that's Bat, Ma, Patakravi, Shred, Taka, me, and Wittacek. Okay. And yeah, this is the, well, general relative case. Okay, so I guess I should say a bit about, well, why this stuff works. So this Heikenshu, well, this p greater than 5 thing came from some Frobenius singularity property. So this is about something to do with Frobenius went in here, and in particular that Frobenius singularities, well, match with KLT if you're in dimension 2. Okay, and so, well, this is essentially why all the positive characteristic stuff started working. Here, if this is spec Z, you don't have Frobenius, so you have to have something else. So the point is, well, due to work of Bat, the Coma-Corliness of integral closures. Okay, this kind of replaces Frobenius, Bat CM theorem replaces Frobenius. Okay, and well, essentially using that, you can define a kind of singularity which also agrees with KLT in dimension 2. Okay, but again, I don't want to talk about flips, so I'm not actually going to go into what details of that. Okay, and then, well, finally, this just leaves one case, essentially, which is the other half of this. So K imperfect in general case, and that was done by, yeah, this here. Okay, so, well, now this means, well, in dimension 3, at least p greater than 5, we have it everywhere it could possibly be had. Okay? Okay, that's a good time to stop for questions. Okay, so, well, I've just listed a whole bunch of generalizations of something. You probably realize why it's useful to have the MMP, but why do we care about all this other stuff? Like, okay, if you only care about C, then okay, maybe you can see what K bar would be helpful for. Then why do you care about imperfect fields? Why do you care about relative situation other than maybe Z? But turns out that you should, and the rest of the talk I want to justify why you should. Okay, so this is, well, section 4, why the generalizations. Okay, so, well, why the generalizations? I guess you should bear in mind the part I'm going to justify through this talk is the base point free theorem. So that's the semi-ample part, not the flip part or the cone theorem or any of the termination. But we're going to be talking about base point free theorem. Okay, and, well, I'm assuming that you only care about algebraically closed fields. Okay, so pretend you only care about algebraically closed fields. Then I'll write down this theorem, which is due to Haken, Witacek, and G. Jouet. Okay, so this is now dimension 4. So assume resolution of singularities. In dimension 4. Not quite. I mean, this is a stronger assumption than you need to make, but this will do. Okay, so just assume resolution holds for all fourfolds. Okay, so then let's see, be a smooth curve over K bar, so smooth curve over an algebraically closed field, and then take a fourfold over this, so xb over c, a projective KLT DLT, q factorial DLT. Just assume I say simple normal crossing. Projective q factorial DLT pair over C, such that the support of, okay, well, the support of some fiber, so I better introduce a fiber, such as the support of X sub S is contained in the round down the boundary, so the coefficient 1 part for some close point S in C. Okay, so you have a setup where you have, well, fourfold over a curve, and your special fiber is contained in the boundary. Okay, so then the conclusion is then you can do an MMP near that special fiber. So then there is an open neighborhood of S in C over which the LMMP works. And I should say, well, over which the KX plus B MMP works. Okay, so in other words, as long as you're assuming this thing about the special fiber in the boundary, you can do MMPs. Not semi-stable, right. This is, so if you start with any pair, regardless of how bad it is, so non-reduced, all fibers non-reduced, stick one in the boundary with coefficient 1, the support, you don't care about what it is as a pullback, then you can do this as long as that pair ends up with the right singularity. So say if it doesn't take a resolution, which you're assuming exists, stick all of it in with coefficient 1, you can still do it. So this is more useful than semi-stable in the sense because you can always get to this setup, well, without semi-stable reduction, which needs MMP. So okay, so right. Okay, and my point is going to be that essentially to do this, you need all the above. Okay, so to get this theorem, you need to use everything up here. Okay, so I'm going to roughly explain the proof of this thing, at least the base point free part. Okay, so we're going to explain the base point free part. And first, I need to kind of well, give you a picture of what this X looks like. So we have the C, we have X over it, which is supposed to be dimension 3. So I'll just draw it as family of surfaces. So then we have this, well, X sub S, which is the special fiber, which you're assuming you put into the boundary with coefficient 1. Okay, and then, well, okay, since we're supposed to only be caring about things in an open neighborhood, maybe I can just localize the base at that point and then talk about the special fiber and some generic point. Okay, so you have a generic fiber, which is a threefold, X eta, and a threefold XS, which look like surfaces, but they're threefolds. Okay, and well then, using this assumption, okay, I'm going to just assume for simplicity that this is irreducible. It may not be in the theorem, but that, okay, just for simplicity, assume it is. Okay, so then, well, the adjunction formula that I wrote down earlier says that you can restrict to this thing. So kx plus b restricted to x sub s is kx sub s plus some boundary bx sub s. Okay, so we get a KLT pair on a threefold over the algebraically closed field ks. Okay, so KLT pair, KLT threefold pair over k bar. Okay, then this one over here, well, this isn't a junction. This is a threefold over a function field, but you can just restrict to the generic fiber and get a threefold pair. So kx plus b restricted to the generic fiber is k of the generic fiber plus b restricted to the generic fiber. Okay, and now we have a KLT pair over, well, k eta, which is, well, not algebraically closed or not perfect, just a function field. Okay, so this is what X looks like. And then the proof of the base point free theorem, well, let me just say, I should slightly reformulate what I called the base point free theorem. So in above setup, if A is ample and X B plus A is DLT and Kx plus B plus A, which I'll call L, is NEF, then Kx plus B plus A is semi-ample. Okay, I just had to reformulate that slightly because well, to avoid some Bertini theorem issues, but it's basically the same as before, but with a B in it. Okay, and this theorem also due to Heiken-Wittejek G. Jouet. Okay, so, well, mostly it's not in their paper, but that's because of the missing ingredient, which we'll get to later. Okay, so this proof. Okay, so proof. So I just need to give you another result, and the proof follows in one line, essentially. So the other result is a theorem of Kashini-Tanaka. Okay, so theorem of Kashini-Tanaka says, well, if X is projective over an excellent Dedekind domain, and more generally, but this is the one we care about, and it removes some other assumptions. So X projective over an excellent Dedekind domain, and L is a NEF line bundle on X such that L restricted to X sub S, let me just say L restricted to F is semi-ample, excellent Dedekind domain of characteristic P. Okay, that's important, sorry. And L restricted to F is semi-ample for every fiber F of X to, well, the excellent Dedekind domain. Okay, then L is semi-ample. Okay, so what this is saying is you have a family, you have an F-line bundle, and it's enough to check the semi-ampleness by restricting to every fiber and then checking the semi-ampleness. Okay, and this is kind of a special to positive characteristic thing. You can't do this in characteristic 0, it's not true. Okay, so this is a special positive characteristic thing, but here we can do that. Mixed characteristic, due to Jakob, you can do a similar thing. So this is roughly the same, except well, I just said it doesn't work in characteristic 0, so that means, well, basically you do the same thing, but you also have to assume that the characteristic 0 fiber is completely semi-ample. So, right, I guess if I'd stated this, the way I stated this, you don't need an extra assumption. The general statement you would. Right, exactly. So if I put residue fields of characteristic P, this also works in this setup, Dedekind domain. Okay, so well now back to where we were. We were trying to prove the semi-ampleness on this in this fourfold theorem. So now we can restrict to the 2 fibers. Okay, then we win because they're both threefolds. Okay, and we know dimension 3. Okay, so then, well, proof of base point free theorem for fourfolds. Well, localize and restrict to the 2 fibers. Okay, they're both threefolds, so we can do that. And now, using the base point free theorem for, well, threefolds over fields, we win. Okay, so we just used, well, this one on the special fiber, and, well, this one and this one on the generic fiber. Okay. So, well, there's still, we haven't used the 7 author thing, so I'll just now need to say, well, where does this come in? Okay. So, well, the thing we just used was the theorem from this year, which is base point free theorem for threefolds over arbitrary fields of characteristic P greater than 5. Okay, so, well, then, right, this is this one. So, okay, the reason this wasn't done, well, back here when we did the pseudo-effective case is because at the time I thought you needed to get some kind of boundedness of the of some del Pezzo surfaces to do it, and essentially here I just don't use that and get around the issue. Okay, so I guess the thing which lets me get around it is going to be this thing, so the relative case. Okay, but I should say, well, here the main point of that paper was originally the arithmetic stuff. It's just a side effect that we prove this also relative characteristic P case even when we don't know. Well, we didn't know this before. Okay, so this was the theorem. The main technical point was, well, we needed this boundedness of del Pezzos, and the reason we wanted the boundedness of del Pezzos was the global ACC for surfaces. Okay, so this global ACC goes into the proof of this thing. Okay, and it's this one that I'm going to kind of justify briefly. Okay, so firstly, what is this global ACC? So it's just, well, it's saying if we take some coefficients, standard coefficients, for example, more generally DCC coefficients that this will do, then, okay, there is a finite subset an ACC subset, gamma, such that whenever we have a projective surface pair, projective over a field of, again, characteristic p greater than 5, such that, okay, so now the actual condition. So I have a pair such that, okay, it's a surface. 2, where its coefficients who come from the coefficient set, coefficients of B are in the coefficient set. And 3, this is the important thing, it's log RBL, so kx plus b is numerically trivial. Okay, so this 3 is the important thing to just set up. Okay, well then the point is then the coefficients of B satisfy ACC. So the coefficients of B come from the finite subset. Oops, this is supposed to say DLT, right? Sorry. Yeah, all are canonical. Yes, they follow from one another. Okay, so well then here you get right. So where are we? I need to say a bit about the proof of this and say why we need the other thing. Okay, Jen? No, it would be if the field were algebraically closed. Right. that was the. So I thought to prove this we needed the algebraically closed. I mean, we needed this boundedness. Then it turns out we don't. I guess that's the issue. But that is its own interesting problem, the boundedness over non-closed fields. So Hiromo Tanaka's got a bunch of work on that, and various other people. Still not known in the low characteristics, in particular geometrically non-reduced ones, and I'm starting to think it's actually false, but I guess that will be found out eventually. Okay, so, well, now, proof of this thing. Okay, so, well, yeah, so the point is here, well, we know this if the field is algebraically closed. This was in Kocher's algebraically closed field paper. So and that uses the elixir of the boundedness of the boundedness thing. So proof known by Becker if k equals k bar. Okay, and so then the point is we want to just reduce to that case. So not use the same argument, but just reduce to it. So, okay, we end up instead, we can assume we're not over k bar. So assume k is not k bar. Okay, but we do have a variety over it, so you can take some finitely many equations. Finitely many equations are defined over finitely many things over k bar. And so you can kind of assume your field is, well, it's the function field of some variety z with z finite type over k bar. Okay, and so then we can do induction on the dimension of z. Okay, so dimension 0, we know it, then in general we'll increase the dimension. Okay, so, well, the idea is roughly, okay, I guess I'm going to try and finish relatively soon. So we have a z, we have a threefold over it. So, I mean, we have relative surfaces, so we have surfaces as our fibers. Okay, and then, well, if we cut down by some random hyperplane here, okay, then cut down by this random hyperplane and localize at the generic point of this. Okay, so what we're left with is, well, we have a special fiber over this KH and a generic fiber over KZ. Okay, and so we can, well, look at, again, a family of surfaces over non-closed fields where this one has a higher transcendence degree than this one. Okay, so this is where the induction comes from. Okay, and so if, well, if we know that we're in a situation where you can already apply the theorem, then, well, then you're okay. Okay, so what we actually have to do is, well, we don't know anything about this one. What we know is, well, we have all this stuff on the, well, the generic fiber. So we have all of this here. Okay, we want to apply induction, so we want to end up with having this stuff on the special fiber. If we have the stuff on the special fiber, well, what is we're trying to conclude? We're trying to conclude that, well, the coefficients of B come from this ACC set. Okay, so then we need to compare the coefficients on the generic fiber and on the special fiber. Okay, so that's a junction. You can always do that. So you restrict Kx plus B restricted to, I guess I'll call it F is Kf plus Bf. And there's a particular formula for the coefficients here in terms of the ones here, and you can relate. Okay, so essentially, if you can put yourself in a setup where this satisfies all the coefficients, all the conditions based on, well, it better be inside here, okay, in order to restrict to it, then you win. Okay, so the thing is you need to, well, do something which lets you assume that this fiber has all of these coefficients, has the right conditions. Okay, I'm not going to have time to actually say how that goes, but I guess what I can say is, well, you do some MMP tricks, and you use MMP tricks. This lets you actually put yourself in a family where all of the conditions are satisfied on these special ones, which lets you, well, pull the coefficients to where you need them to be. Okay. Should probably stop here.